Yeah.
Great. Hi, everyone. All right. Well, happy to have Mika. Anytime you want to come, you can come. Mika needs no introduction, so I already introduced him last time. I will not introduce him, apart from the fact that he's amazing and I'm a huge fan. And he will tell us about constant cost communication.
Okay, thank you. So this is trying to work with some people from Ohio State, and then this guy Nathaniel Harms, ex-Waterloo person. How do you say Waterlooian? Waterloodite. He is a Luddite. He uses fountain pens for notes. Okay, so I kind of want to start by just gauging how people in the audience know communicate, basic two parts of communicative complexity. So here's like a sample puzzle. So I have Alice and Bob, and they're given n-bit strings, and they're communicating over a shared communication channel. And I just want to know whether the two players are given the same input. So maybe you could think of X and Y as being like terabytes worth of databases separated by a long distance. You want to test whether the databases are consistent. So if I gave you this as a kind of a coding interview question, how would you attack a question like this? I'm sure some people are experts, but if you feel like it's not trivial to you, like how would you approach, I want to know, a setting like this? It's maybe under-defined question, but that's how coding interview questions are. So there's no right or wrong answer. We can just start discussing it.
Error correcting code.
Okay, so you want to take n bits and apply an error correcting code? Yeah,
You want to query an extension of X and an extension of Y and check that they're equal?
Okay, so maybe something like that could work. You could say, let's encode them using an error correcting code. So maybe the length blows up by a constant factor. And now you know that if they're different, then they're different in a constant fraction of places. So now you could maybe just compare a random bit. I'm sure this is what you had in mind. So that's one way to do it with randomness. But actually, it's very basic, like maybe some of the first theorems in communication complexity is that if you try to do this deterministically, you can't do anything non-trivial except just to send the whole input across. But as we said, if you're randomized, then you can get a huge speed up. And this is a huge gap between deterministic and randomized. So it's just an example that really shows the power of randomness. So this is such an important example. I'm going to spend some time discussing it. So just that we have a really like a low level understanding of what's going on here. So this is called the equality problem. And I've just written down here the truth table of the function. Sometimes it's called the communication matrix. So it represents the problem in the sense that I think of Alice as being given as input a row, and Bob is given as input a column, and then they just want to compute the value and the corresponding entry in the matrix. So for equality, I want to test whether the row index and the column index are the same. So you only have these yes cases on the diagonal. And okay, so this is, by the way, it's an exponential size matrix because these are all of possible Alice's inputs. So there are 2 to the n of them. And in fact, if I give you any Boolean matrix, you can think of it as defining a communication problem. So Alice gets a row, Bob gets a column, and you have to compute the value in the matrix. Okay, so how do we solve this using a randomized protocol? So, so I'm allowed to use like public shared randomness. And I'm going to describe a slightly different protocol that we discussed. So another solution is maybe you compute a hash fingerprint of your input string, and you just send the hash value across and you compare.
Some people from Zoom are saying that they can see the slides changing.
So from if you just restart.
Okay, how about now? Okay, somebody says it's working now. Okay, so my hashing protocol, I could visualize it as follows. So I'm going to choose, if I'm Alice here for a row, I'm just going to, my index row, I'm going to just choose 2 random bits for it as a hash function value. I'm going to use the same values for Bob. So the ith column and the ith row, they're going to get the same randomly chosen hash value. So, you know, this randomness comes from some public string that's written in the sky. And, you know, for the ith input, the players just look at the ith pair of random coins from the public source. And so concretely, the protocol just is, you know, you look at your pair of the bits, you send that across that 2 bits of information, and then the other player just compares that hash to their own value, and 1 more bit says, do the hash values agree or not? So if the pairs were given equal inputs from the diagonal, then the hash values are always the same, you never make an error. Okay, if you're off the diagonal, non-equal values, then the hash values might collide erroneously with error 1/4. So really, with just constantly many bits, you get a constant error protocol. Questions about this basic example? Okay, so the whole kind of main research question for us is, well, what are the problems in two-party communication? Actually, has constant hops. So this is like very extreme, hyper-fast protocols. And so there are a bunch of reasons I liked this kind of a question. So one is I did my PhD in communication complexity. The most classical questions, we often think if something has polylogarithmic complexity, it's sort of efficient protocol. If it has polynomial or even linear in n, it's inefficient. So haven't really explicitly looked at constant cost protocols. I would, years ago, would just lump constant cost amongst with polylog cost and be done with it, and not really appreciate that there's maybe something interesting happening. And if you really want to pin down, explore the quarter of constant cost protocols. So these questions are kind of a new question. It only arose in the 2 or 3 years ago. And so it's a new perspective. Again, maybe I would have thought years ago that there's nothing there. Like, okay, we have equality, but what else can we do? And now we have this growing body of work saying there's interesting stuff happening in this corner. So it's an interesting perspective. Also, what I really like about this is that all the tools I would have developed in my PhD, they're useless here. So I can't use any of my usual tricks. Kind of just have to start from scratch to understand this perspective. So it's refreshing. And yeah, it's true, and you'll see today, very few examples of problems I know that do have constant cost. So we need more examples. And again, I think there's like much to be done to figure out what's going on here. So many open problems, which is what I'll end up with. Okay, so let me start with showing you a bunch of problems that in fact do have these super efficient algorithms or protocols. Although I'm going to let you give me the protocol. Let's try it this way. So here's one problem. It's called the tree adjacency problem. So I have some kind of huge tree graph. It's known to both Alice and Bob, or n nodes, n is huge. And then as input, Alice is going to get a node of the tree, Bob is going to get another node of the tree, and they have to decide whether they're adjacent in the tree or not. So I claim this problem, testing adjacency, admits a hyper-efficient communication protocol, randomized constant cost protocol. So anybody want to try how to design adjacency test? I give you a hint. Equality has a constant cost product, we just saw. So if Alice and Bob are thinking of nodes in the tree, you can efficiently test whether they're thinking of the same node. Although I'm asking you to tell if they're thinking of adjacent nodes, so you have to do something. But I'm allowed to use equality tests.
Is it a constant degree tree or not? Degree is.
We can discuss constant degree case first, if you want. So if it's constant degree, I guess,
Then deterministic, you can do it. Probably.
yeah, everything's randomized for now.
Yeah.
So everything randomized. And the key is, I know equality testing is constant cost.
But they're adjacent only if one is the parent of the other, right? So you want to check the parent circle. Like,
Yeah.
the parent is equal to one of them.
Yeah, so you think of the tree as rooted, like I've drawn it here. And then both players can just, they know their parents. So they would test, is my parent, Alice's node, or is Alice's parent Paul? That's two equality tests. So when I was making the slides, I was really trying to phrase the protocol so that at one point you would check whether Bob's your uncle. But I couldn't. I couldn't. So maybe you can help me. But yeah, the punchline is this is another constant cost problem, and it was slightly non-trivial to find this. So you pass the first quiz. Second quiz, more difficult. So now planar adjacencies. I have a huge planar graph, and the same question is players are given nodes. How do they tell whether they're adjacent? So I give you a hint. Tree adjacency has an efficient protocol, like we just saw. So maybe you can use tree adjacency here somehow.
Because you can do it for bounded arbors if you have this one. You just partition your graph into trees.
Yeah.
For every one of the trees. Yeah.
Yeah. So planar graphs happen to have arboricity 3. So they're unions of for very precise not trees, but forests. But our tree adjacency actually works for forests immediately. So this is a structural result that says, actually, this problem also reduces to the previous case we considered. You just do tree adjacency in each of the 3 forests. Okay, so another constant cost problem. Okay, so this is kind of fun. Quiz number 3. So this is a pretty well-known problem, actually. So it's called the one Hamming distance problem. So here, Alice and Bob are given n-bit strings, and you want to decide not whether they're the same, but whether they differ in exactly one coordinate. So this would be a yes instance, because there's only one bit where they differ. I could equivalently ask whether it's the same as asking for adjacency in the hypercube graph. So I'm sure some people have seen this, but can we attempt to find a constant cost protocol here? So we know equality can be tested efficiently, but now I kind of want to know, can I test for having one difference efficiently? How would you approach this?
Do you get logarithmic from the arboricity thing?
So you want to decompose the hypergraph into log n trees. I don't know what is the arboricity of the cube.
It's almost log n because the degree is log n. So.
Okay. Oh, it's log, yeah. So yeah. So 2 to the n sized graph. But we can do. I don't want to solve this for you, but there is a log n bit protocol where you just binary search for the difference. Like you could test equality on the left side and just zoom in on one difference. And then I guess once you find one difference, you test that the rest of the string is equal. But that's log n cost. I want constant cost.
You can do this trick. People do it as zero samplers. You just partition randomly into 2 parts. Then you run quality tests on both of them.
Yeah, that's exactly right. So you partition the strings randomly. Okay, not into contiguous pieces, but no, let me just, for illustration purposes. And so there's a random partition, and then you just expect to find that exactly one of these parts yields an equal instance. So one is equal, the other one is unequal. So if there were 2 differences or more, then there's a constant chance that your partition has differences in both sides of the partition. Okay. So we can also study, okay, so that's our constant cost protocol. You can also study generalized version where you're looking for k differences. K coordinates are different. You can still do it with constant cost. Now you just have to partition into roughly like K squared buckets. So you'd want a buckets that avoid a collision, like two differences in one. So if you do like K squared buckets, then the paradox says you isolate all the differences into different buckets. And in fact, okay, so this has been studied a lot, this problem. Recently, it was even pinned down the exact complexity of the K Hamming distance problem. So it's K log K. I mean, the upper bound is old, but we have a matching lower bound.
Is this a promise problem, or are you just considering like difference in one coordinate versus any?
Yeah, so everything's a total problem. So the yes case is when there's a unique difference, everything else is the no case. Yeah. Okay, so this says if K is a constant, we get a constant cost problem. Okay, so we could do one more example. So what do we do? Hamming distance, but not for Boolean strings, for strings with a large alphabet. So we have strings with alphabet size 4. And I still want to decide whether there's exactly one position whose symbols are different. Well, the same protocol from before still works. You could randomly partition this into a few buckets and then test it for equality, expect to find only one bucket that's non-equal. So the same protocol works, but let me do it a bit differently. Let me say that actually the large alphabet case reduces to the Boolean case. So there's a nifty reduction. So I can rewrite the string here as just a bit string where I replace each symbol with 4 bits, and it has a 1 index, exactly 1 coordinate. It just indicates which symbol I use. So A was the first symbol of my alphabet, and more generally, I'm going to get all zeros except 1 in the ith position for the ith symbol. So that's some kind of a unary or indicator encoding. And it has the property that if there's one difference here in the original input, in your binary string, you're going to have 2 differences. So in fact, it's a kind of a reduction that says you can solve the large alphabet case, rewriting your input in a Boolean, and then doing distance to Hamming distance to protocol. Okay. More examples? We like it.
Here, the size of this problem, especially because it's constant size, it's neat that the size of the alphabet doesn't seem to matter.
Yeah.
Can it be infinity?
Yeah, you could have. Okay, I
How
don't.
much can it be?
Yeah, you could have any size of alphabet. It could grow with the size of the input, and yet the reduction still works. It just alphabet size is K. You would have length K blow up in the encoding size. But what you're maybe getting at here is that, yes, in the reduction, I blew up the length of the input, but because everything is constant cost, it's like, I'm allowed to do that. Constant is constant. Okay, so let me give you one more example. It's a non-example problem that does not admit constant cost protocol. So another classical one. So here, Alice and Bob have numbers from 1 up to n. What I know is Alice's number is at least Bob's number. So the communication matrix looks very simple. Again, row and column indices, you just want to test whether you're in the upper or lower triangle. So it's relatively well known that this problem, its cost is non-constant. So it's actually pinned down to be log n. But I mention it as an example of a problem that's very simple. I mean, the picture is simple, but also there's a technical sense in it in which it's simple. The VC dimension, the problem is a constant, and well, something called sign rank, we could not define it, but the matrix also has constant sign rank. So it's simple in many ways, yet still not constant cost. So this is just useful to keep in mind if you want to understand which problems have constant cost. Well, I can't piggyback on like other known complexity measures, they don't characterize this notion of being constant cost. Okay, so that's enough examples. In fact, that's all the examples. I showed you everything we basically know. So I wish I could give you more examples. I like going through them, but that's it. I say essentially the only examples, which I can make more precise by, let's just discuss a little bit. How do we impose more structure on this like jungle of examples? Try to make sense of this landscape. So we already implicitly used the notion of reductions between problems. So planar adjacency kind of reduced to 3 instances of tree adjacency. Tree adjacency itself was solvable by invoking equality protocol twice. And you can even make this formal. You can define the 2 communication problems, they reduce to each other if I can solve problem A by making, so by a deterministic protocol, doesn't use randomness, and then it makes constantly many oracle calls to problem B. Let me say that more formally, or through a picture. So what is this deterministic oracle protocol? So I want to solve A by the following kind of protocol. So the input to A is X for Alice, Y for Bob. And now Alice and Bob, they can query this Oracle B that lives in the cloud. It's like a cloud service provider. So you can submit queries to the cloud. The players can locally compute any function of their inputs. So Bob looks at Y, computes anything locally from it, and submits this input to the cloud. And both do it simultaneously, and the cloud just responds yes or no. Like, is this pair X prime, Y prime, is that a yes or a no instance of problem B? And so this is just unit cost, and you can do constantly many such Oracle queries. So I could also allow the players to send constantly many bits to each other, but it wouldn't affect the definition. You can simulate sending of a bit through the Oracle. So that's kind of the formal definition of a reduction. Not like super important, we have an intuitive notion of what it is. It's just that if I not rule out reductions, then we have to have a formal definition. Questions about this notion of Oracle reductions?
So under this definition, what we did for Hamming distance it wasn't a reduction.
It was, so let me repeat that this computation could blow up the length.
But it was randomized. When we did the Hamming, like we partition into 2 parts random.
Yeah, okay, that protocol where you did random bucketing, that, yeah, used randomness there. Yeah, good point. Okay, so these are actually formal reductions now. And okay, let me ask, can you reduce, just to complete the picture, can you reduce equality to planar adjacency? And we make all these problems equivalent. So you give an X and Y, X and Y, they want to test, are these guys equal? Can I transform this into a question about whether nodes are adjacent in some planar graph?
The graph can just be the bipartite graph of all the strings, and X is connected to X.
Yeah, I would say what is the graph you're testing adjacent? It's a matching. So you just have one isolated edges for every possible n-bit string. So these problems are actually all equal. So you thought I have many examples. I have even fewer examples really than what I showed you. They're the same problem. Okay. We also saw this one Hamming distance problem. Well, I claim that equality reduces to one Hamming distance. Why is that?
So if the input is n bits, then you make it n plus 1 bits and x is connected, x with 1 is connected to x.
Yeah, so I guess x and y, you just append a different bit at the start. Okay, so you know, x and y are equal if and only the Hamming distance is 1 for the oops. Okay, so yes, there's certainly a reduction this way. More generally, k Hamming distance reduces to k plus 1 Hamming distance. So the Hamming distance problems kind of, they form this hierarchy. And so it was recently showed that actually that this is strict. You can't have a reduction the other way around. So you can't solve one Hamming distance by a bunch of like a protocol that queries an equality oracle. And as Sepra was saying, the protocol here did the random bucketing trick. And that's something turns out you cannot simulate with if you just have access to equality. So okay, we at least have two different problems in this landscape of constant cost communication. And so more recently, this is from Stock this year, Nathan and co-authors, they show that the Hamming distance problems actually do yield an infinite hierarchy. So if you increase k, then you get a new problem. Maybe I'm lying a little bit here. Maybe they don't quite get a separation between any two adjacent values of k, but it's an infinite hierarchy nonetheless. They prove something a little bit more general, and this is how their paper is titled, is that there is no single problem that is complete for constant cost communication. So what it means is that if you fix any constant cost problem, then you can find the k large enough that the k Hamming distance does not reduce the problem you started with. So, it's a bit of an abstract statement, like start with any constant cost problem. We don't actually have any other examples besides the problems in this hierarchy. Like any example we had of a constant cost problem lies somewhere in this hierarchy. Which prompts this question. I mean, we don't have examples. Are there more examples? Or could it be the case that actually every constant cost problem just lies somewhere in the hierarchy? That Hamming distance is basically the only thing you can do with in constant cost. And okay, so yeah, one of the kind of phenomena that's plaguing this area is we don't have much examples. We only have few, and then you can make these outrageous conjectures based on just having few data points. So this is one such thing, like maybe everything reduces to this because we just don't know about the problems. And I mean, there's some validity to this. I mean, we've had decades worth of time to come up with more natural problems that would have constant cost, and it just hasn't materialized. And so okay, I should also mention, only recently when people have really focused on constant cost setting, there are loads of works that, yes, do find these constant cost problems. There's, I think Nathan has a paper where they show that distance gate connectivity in Cartesian products of planar graphs has constant cost. So they get very involved, yet even those protocols, they reduce to some Hamming distance oracle. So at least, Nathan says it was conceivable that this is all there is. But okay, today I want to show that our new result says that there are more examples. So we devise a new constant cost problem that doesn't reduce to this hierarchy. So it's one problem such that no matter which k you choose, you can't reduce that problem to k Hamming distance. And I'm sort of suggesting already that the problem we came up with is slightly artificial. Again, like, you had to kind of sit down and construct such a thing because we don't have natural enough examples.
Question here, so all the problems that you showed us, they are also one round or one way communication.
Okay, good question. So you can make any interactive protocol one way with an exponential blow up in cost. But constant turns into exponential cost is still a constant. So this is the kind of weird logic you encounter in this corner of the world. Okay, so this is the main result. But actually, I also like even more maybe the way we're going to prove this irreducibility result. That's going to involve an interesting coding theory puzzle. And it's actually how I got interested in this project. Nathan told me about this puzzle, and I was like, this is like, should it be solved already? Let's just Google it. But okay, maybe, I don't know how to Google it, and we ended up approving some lemma encoding theory. I'm going to get to that. So let me just show you what is the problem, and let's analyze it. So as promised, it's slightly artificial, but let's approach it slowly. It's some version of Hamming distance. But the inputs now, they're Boolean matrices. Okay, so Alice gets an n by n Boolean matrix, similarly for Bob. And then I want to decide whether the two matrices are related in the following sense, in the 4-4 sense. So I want that this is when you should output yes. The yes case of the function is when, so all of the rows are equal except two of them. So there's some two rows somewhere in the matrix such that, this row has distance 4. There are 4 differences for this row. And then another row with also distance 4. Okay. So again, the two matrices in the yes case, they should have Hamming distance 8, okay, 4 plus 4, 8. But I also want that the differences are split so that one row has 4 differences, another row has 4 differences. Okay, so this is the problem I claim is a new problem. I want to claim does not reduce to Hamming distance, yet it has a constant cost still. Can you tell me how to solve this with a constant cost protocol? So it's not an unfair question. You've seen enough tools to piece it together.
One idea that comes to mind is encode all the rows and columns with codes.
Okay, you like error codes. Okay, I mean, we could try to do that. So what then?
And
so
then,
you've now blown up the distance that's presumably 4 into something that's even a constant fraction.
yeah.
In the PR code, like distance 4 should go to a very fixed distance, and then you cannot estimate it exactly.
Yeah.
I think you can just do bucketing again, like 2 levels now.
Okay.
Focus on the rows, partition rows into 2 different blocks. Let's see if it works. So,
Okay,
and
so
then check, yeah.
So let me maybe just add a bit of structure. I mean, this function has like a couple of properties. It first claims there's exactly 2 unequal rows. So the bucketing thing at least can check that. Like if you bucket the rows randomly, let me just maybe, here's one bucket, here's another bucket. Well, okay, I have claimed 2 unequal rows. So maybe I need like 2 squared buckets. And then I just like do equality for each of the buckets. And I expect to see exactly 2 buckets that are unequal. So, okay, I can test, there's at least 2 different rows that are unequal, but I still need to know that, okay, they're unequal, but the distances are 4, 4.
Now, do you want to, after the getting pocket column wise into 5 pockets? If I look at matrix A plus B, I should only see a small number of non-zero entries. No, it's like an entire, all zero matrices except for 8 entries.
Yeah, so X and Y together, you're expecting to see 8 ones. You want 4 of them to lie on one column, 4 of them to lie on another. But we've already checked that there's exactly 2 unequal rows. That was what the bucketing told us.
Yes.
So if I know that, I guess I can also check, let's just throw in checking that the global distance is 8. So what are the options that remain? Well, global distance is 8, but you don't quite know whether it's 4, 4. It could be 2, 6, or you have still a few cases to consider. Maybe I'll just tell you, I mean, it's not hard. Another bucketing, and yeah, so maybe now I just do 2 buckets, this randomly chosen, and I test that the distance here and here is 4, and here is 4. So the idea is that there's a constant chance that the 2 unequal rows are bucketed differently. So buckets have distance, both distances 4. That's it. So this was the whole protocol. So we first checked for 2 unequal rows, and then we just partition randomly and expect to find 4 distances 4 in both buckets. Okay, people buy this? Okay, so this was easy. I mean, it's non-trivial to come up with these problems, but the real technical difficulty is showing that this problem does not reduce decay Hamming distance. That's the main technical claim of the paper. So we'll get towards that. For now, I wonder if there's a nagging question about why 4, 4? Is that nagging you? Because I want to discuss a little bit why did we choose, what's the significance of these distances 4, 4? And just to kind of illustrate this problem a little bit. Well, the short answer is this is the simplest case where the main theorem is true. So if I try something similar with distances maybe 1, 1, then it doesn't work. So let's see why. So let's study the 1, 1 Hamming distance problem. Okay, so again, in the yes case, I'm expecting 2 unequal rows, and you should have distance 1 in both of them. So okay, it does admit a constant cost protocol like before, but now it also admits a reduction to Hamming distance. So should we try to find this oracle protocol? So remember previously there's a couple of conditions again in the function. There's the sort of the initial check where you want to make sure that there are 2 unequal rows. So that you can do with the large alphabet Hamming distance protocol. So you can think of each row as a symbol in an alphabet. Okay, the alphabet has 2 to the n symbols, but so we just view these matrices as a sequence of these row symbols, and I want to check that there are two symbols that are different. And I showed you how this kind of large Hamming distance problem reduces to just Hamming distance using this indicator encoding. So okay, I can check that there are 2 unequal rows. Well, how do I check that there's a distance exactly 1 in each of them? What kind of a Hamming distance query should I do to make sure that the 2 unequal rows are both at distance 1?
So when you do the Hamming distance on large alphabet, you will not be able to figure out which index they are different. That's log.
Yes, so it's good intuition to think that in constant cost, you can never find out where the difference is. That's intuitive, like log n bits of information. So you can at most like intuitively like know, do constantly many buckets and know unequal buckets, but you can't really find the differences ever.
If you define a graph on your large alphabets and check adjacency in that graph, so all of these strings will result in like a bunch of alphabets, and two alphabets are adjacent if they differ in one binary bit. And so you not only want to check if the two strings differ in two alphabets, but the two alphabets are adjacent in the graph.
So, okay. I wonder if this is what you're saying is you just, because this is the solution I must be looking for, you just globally check that the Hamming distance is 2. Okay. So it's globally it's 2, and I have 2 different columns. It must look like this. Okay. So that was the oracle. And again, this was doable by a reduction to a Hamming distance query, and this is very explicitly a Hamming distance query. Okay, so one Hamming distance is nothing new. It just reduces to old stuff. Well, let's make it more complicated. Let's try 2 Hamming distance. So same story. 2 unequal rows. For each unequal row, I'm expecting distance 2. So this is a bit trickier. We can still reduce it to Hamming distance queries. So let's do the usual. Let's first check 2 unequal rows. We can check global distance is 4. So that gets us, we know that either we're in the 2-2 case, which is what we want to check, or we're in this 1-3 case. So what remains is to tell these 2 cases apart. And the trick here is to kind of exploit parities, even numbers here, odd numbers here. So what we can do is we can just, Alice could compute the parity of every row and store it in this vector x. So x is some little x. Okay, I'm not going to compute the actual parities of these rows, but yeah, you record the parities here. You do the same for y, and you just check that those 2 match. So that means that every row, its parity for Alice matches the parity for Bob. So if 2 strings have the same parity, their distance has to be even. So now you check that all of the row pairwise row distances are even, and that rules out this case. Okay. So again, we're doing an equality check, which is in the Hamming distance hierarchy. So still not a new problem. What about 3-3 Hamming distance? Well, actually, we believe that the result already holds for 3-3, but it's technically easier to just go to 4-4. Okay, so I now want to try to solve the main result, that the 4-4 version just does not reduce to the previous hierarchy. And the key is, again, this coding lemma, which I really like. So now if you've not been following, you can jump back on, because my coding lemma is completely like independent puzzle that requires no background. So this is what Nathan asked me. So for now, let's leave constant cost behind, and let's just like do some coding tricks. Okay, so here I define this notion of an F code. So I'm looking at encoding functions that take n-bit string and encode it by some other string. And I'm interested in encodings that transform like small Hamming distances consistently. So I have some f, it's an arbitrary f, so it tells me how distances 2, 4, and 6 should be transformed. So I want, I have an F code if whenever I start with some prescribed distance between x and y, so, either 2, 4, or 6, whenever I have 2 strings for that distance, the encoding map maps them to such that the new distance is given by f of the original one. So picture. So I have X and Y, and their distance is some D. And okay, so I'm interested in the cases, these cases. And then I apply E, so encoding function to both of them. So I get E of X and E of Y. And now the distance D becomes F of D. Okay. And I only have this constraint again for like small Hamming distances. So again, I'm looking at these encoding functions that have the guarantee that small distances are consistently transformed. And the question sort of is, okay, like what kinds of codes like this can exist? And our main coding lemma now is, okay, so
was F arbitrary there? You were given the F or you picked?
so F is, for now it's arbitrary. So you fix an F and then you can say something is an F code. So now I'm saying, suppose I have some F for which I get an infinite family of F codes. So this F is kind of implementable for arbitrary large strings. Then I say, oh, only very specific Fs admit such infinite families. The F must be affine. So, you know, the values, all of these values, they must lie on a line. They're an arithmetic progression. So you can't have F codes for arbitrary F. The only codes that exist, actually, the distances are scaled affinely, linearly. And okay, to really make sense of this, I'm going to give you examples to make it a bit more concrete.
Sorry, and that E can be any code, like non-linear codes or anything, right? Just be any code.
Yeah, it's any function, although it does have the property that small distances are perturbed in a consistent fashion.
But I guess the lemma kind of says E has to be affine or something.
Oh, no, it only says that the distances are affine, not that the, yeah.
And why 2%?
Okay, let's see. I really have to see some examples to make more sense of this. So let's see. Now here's one code. It's the repetition code. So it takes n bits, outputs 2 n bits where you just replicate the thing. Okay, so you know this is an infinite family of codes that exist for any n. What is the associated f? Well, I mean, in all cases, if distance is 0, it comes up 0. But then distances 1 become distances 2. So it's like doubles distances, right? So that's a valid F code family, and it is affine, like predicted by this lemma. So, okay, this example did not break our lemma. Let's see if we can break it using other examples. So here's another code, indicator code. We've sort of seen this before. So this code maps X to the X, the basis vector. So the output length is exponentially long. This vector is all zeros except it is a 1 in X position. Okay, so we saw this previously when we were reducing large alphabet Hamming distance. So this is also an F code family. So 0 maps to 0, but any other non-zero distance becomes 2. So the plot looks like this. So now note, this is not an affine function, but it is affine if you restrict it to 2, 4, and 6. Okay, so the lemma wasn't broken because I'm only interested in these values. So a final example, we've also seen this, it's the parity code. So I map n bits to just 1 bit that records the parity of the string. So Again, it's an infinite family, and that values are like this. So very non-linear, but if you restrict it to even values, it's fine. Okay, and I mean, I hope you see that these encodings we've seen implemented in protocols. So our lemma somehow has to adapt. Okay, and so there are no more examples. Our lemma essentially says that these are the only examples. You can combine different examples, and you can even like add noise to the codes that distort large distances. But as long as it satisfies these local conditions, then you have to be affine. Okay, so this is where we want to go. I'm claiming that this interesting coding lemma is somehow relevant. They're equivalent. So that's a bit surprising. So we'll eventually use the non-existence of non-affine codes. So every code is affine to show you can't have a reduction. And that's the non-trivial part of the paper. It uses many pages of Ramsey theory. So you prove this direction to prove the main theorem. Really, you prove the contrapositive. You say, you know, what if there is a reduction? You look at the Oracle protocol, you look at what kinds of queries to the Oracle are being made. That's like your encoding function, like what are the queries. And from a hypothetical reduction, you can extract, using Ramsey theory, a infinite family of codes that's not affine. So that's the non-trivial part of the paper. But for now, just to kind of illustrate, I want to give you the other direction, saying that this coding lemma is necessary to prove the main result. So if there's no reduction, the coding lemma has to hold. So that's easy. I want to show at least, and then I end show having some. So I'm going to show the contrapositive. If there are non-affine codes, I can give you a reduction. Okay, so again, suppose coding lemma is false and I have these impossible non-affine codes, then I'll show you a designer reduction. Okay, so we're trying to solve this 4-4 problem. So we do the usual steps as before. So we want to decide the yes case was where distance 4, distance 4. Okay, so I check 2 unequal rows. That was doable with a Hamming distance query. Total distance is 8. So now these are the cases that remain. The 2 unequal rows, the distances are split like that. I do the parity check. I can rule out cases, these sets that have odd numbers. So, I mean, this is all we've seen before. So now I'm just left with distinguishing between 4, 4 and 2, 6. Okay, how to distinguish between those two cases? Well, I use my impossible codes for this. So I encode all of the rows of the matrix with my non-affine code. So it looks like this. I apply the code to all of the rows. So the 2 distances, they started out as 4. Now they become f of 4. Okay, so my check here is I want the distances of the encoded matrices to be 2f4, okay, like in this picture. So certainly if I'm in this case, this check will pass. Okay, what if we're in this case? Okay, so suppose I'm in the other case, so that distance is 2, that distance is 6. Okay. Okay, when I apply the code, I get f of 2, f of 6 are the new distances. What is the distance between the 2 encoded matrices? Well, it's the sum of these two, f2 and f6. But it's a non-affine code. f2 plus f6 is not twice f4. Okay, so that was the easy trick. You have to prove this kind of coding theorem lemma in order to rule out this reduction. So, okay, so I wanna end here quickly. I've used up my hour. So as I was sort of alluding to, this is an area which is like rife with open problems, and I'm excited because there, like, I can't just use my existing tools. I just have to, yeah, like start from scratch. It also means that some of these problems could be very difficult. So we lack examples. We know there's no single complete problem, but maybe there's a hierarchy of complete problems, like the Hamming distance hierarchy could have been complete, yet we show it wasn't. Or maybe if there's no complete hierarchy, maybe there's still some combinatorial characterization for when a problem has constant cost. I don't know whether to believe that or not, but if there was a simple characterization, it would tell you a lot about the structure of constant cost problems. You can try to understand some of that structure, even if we don't have nice characterizations. So, for example, there's one question about a constant cost problem. Does it always have like a monochromatic submatrix of constant fraction of the matrix? So all ones or all zeros. It's like these are all the examples we know of. They do have large monochromatic rectangles, so you might conjecture everything has. Yeah, again, you can make these outrageous conjectures just because we have a Lagrange example. So one such conjecture is if you look at constant cost protocols, and then there was this constant sign rank thing. Their intersection currently just has the equality problem, and also therefore everything that reduces to equality. So hey, maybe this intersection equals everything that reduces to equality. And even though it's kind of silly to believe these statements just because of lack of examples, at least it gives you direction to disprove this. Find examples, more examples. Okay, so the low topic, or actually, if you want to look into it, I recommend this this recent survey by the Hatami brothers. They have here a very nice diagram of some of the classes we looked at. So there's your constant cost class. Here is the class of all problems that reduce to equality, and constant sign rank, and they have done the work of finding out which relationships are unknown. So that's a good starting place for more problems. Okay, thank you.